going to continue on with our coverage and heat exchangers. Oh, looks like my battery has run out on my pen. Let me get back. I'm going to have to go grab some new batteries for my my pen for my tablet. But we're going to get into how to work some or go through a heat transfer analysis of heat exchangers and how to calculate heat transfer rates, temperatures associated with the hot and cold fluids, and and be able to compare heat exchangers based on their performance. But give me a couple of minutes. I've got to go grab some more batteries for this pen, and I'll be right back. Should take about 3 minutes. All right, so let's get to it. I'm going to start sharing my screen here. Let's see here. Well, let's see. Close and restart that. There we go. All right, so the last time we were talking about these heat exchanger configurations, the counterflow, we have the counterflow and the parallel flow double pipe heat exchangers, which are basically just a tube in tube. So when they say double pipe, it's just an annular configuration. So when you're looking at it from the end, there will be an inner tube and an outer tube. And typically, hot fluid would be on the inside and the cold fluid on the outside. It can be in the opposite direction, but typically, since the heat transfer will occur between the two fluids, you have the hot fluid on the outside and you have environmental conditions on the outside. Typically, the hot fluid is at a much higher temperature than the ambient. So if you put the hot fluid on the inner tube, the heat transfers to the cold fluid, and the temperature difference between the cold fluid and the ambient is much less than the temperature difference between the hot fluid and the ambient. So you minimize the amount of heat transfer that will be occurring between the fluid flowing on the outer pipe and the ambient here. But for any heat transfer analysis on a heat exchanger, we're considering that all the heat lost by the hot fluid only goes into the cold fluid, and the cold fluid is only gaining heat from the hot fluid. So basically, we have this insulated condition that we're considering around the entire heat exchanger. So the only heat transfer that's occurring is that heat transfer that occurs between the two fluids. So we have, if we have a double pipe heat exchanger, it's either going to be parallel flow or a counterflow heat exchanger. For the cross flow heat exchanger, which is like the radiators or evaporator or condensers of your air conditioning system, consists of tubes, typically with fins on them, such that if we have fins that confine the fluid flow, that is typically a gas over tubes, this will be considered both fluids being unmixed, in that the fluid that moves through the tubes is always unmixed as it moves through the heat exchanger. And because the other fluid that moves over the tubes is confined to spaces in between those fins, it will be considered an unmixed flow arrangement for both the cross flow and the tube flow here. One fluid mixed and one unmixed. The unmixed one will be the tube flow, and the mix would be the fluid or the cross flow that flows over these tubes. And it's considered to be mixed when there isn't a defined pathway for the fluid that's moving over those tubes there. Now, these designations are important because some of the expressions that we'll use to calculate heat transfer rates or performance, or maybe to calculate a temperature, the definition of the relationship between the heat transfer rate and the temperatures that will exist in the fluids is going to be based on the type of heat exchanger it is and what the flow arrangement is. And then finally, we have the shell and tube heat exchangers, which are typically used to provide cooling for air as a chiller, such that if air is moving through the tubes, cold water can move through the shell, so that heat exchange is occurring between the two fluids through the tubes that are actually here that are flowing in the heat exchanger. Now, for these shell and tube heat exchangers, the flow arrangement is going to be a function. The flow arrangement can be defined, or is defined, based on the number of shells and the number of tubes. So here, this is one shell, in that there's only one pass through the shell where the fluid comes in and goes out. And this is two tube passes. Now, there's only one tube here, but it has two passes. And those passes are based on the length of the shell through which that tube is moving. So it moves once, or the fluid that's moving through the tube moves once down the length, twice down the length. So this would be considered two tube passes. And this heat exchanger is still really only one shell, but there are two shell passes, in that when we look here at this fluid that moves through the shell, it comes into the shell, moves along the length of the shell, and then moves back along the length again. So it has two passes through the shell, because this green line here, or this green bar, is a baffle that requires so that the fluid can't just move from this inlet to this outlet, which would just be a straight line, but the baffle makes the fluid through the shell move along the shell length twice. This would be considered 4 tube passes, because it moves along once, twice, 3 times, 4 times here. The thing to consider about the tube passes, these typically are in multiples of 2, in that the fluid that moves through the tube, or the tube arrangement, will be such that they come into and leave on the same along the same length, or at the same end of the shell. So here, this would be 4 passes here with 2 shell passes. So again, this designation, or this identification of the number of shell passes and the number of tube passes, is going to be important for the expressions that we'll use, again, that relate heat transfer and temperatures associated with the heat exchanger. Now, there are other types of heat exchangers, but these three types, the cross flow, shell and tube, the double pipe, are the ones that are actually presented in the text. Now, no matter what the type of heat exchanger is, there's always heat transfer between the two fluids. So for any heat exchanger, there are two fluids. Again, the hot fluid and the cold fluid. The heat transfer rate from the hot fluid will just be defined as the mass flow rate of the hot fluid times the specific heat times the change in temperature, where this will be the inlet temperature minus the exit temperature for the hot fluid. Because that hot fluid is going to lose heat as it moves through the heat exchanger. Now, with this being the specific heat for this is a liquid, the specific heat, that is the constant pressure specific heat and the constant volume specific heat, are actually the same value if it's considered to be an incompressible liquid. Also for gases, usually for a given temperature range, the specific heat will be considered to be a constant, but if it's a gas, the constant pressure and constant volume specific heats are not the same. And since it's a flowing fluid, the expression of the specific heat as C sub P to represent changes in enthalpy is what's required. So you'll see in your text, instead of there just being a C here, this will be C sub P, so that it considers that we can have a gas or a liquid that is moving through the heat exchanger, such that if it's a gas, we're definitely going to use C sub P, because there is a difference between C sub P and C sub V. C sub V would be used to calculate changes in the internal energy, but since it's a flowing fluid, we also have to take into account the flow energy. So we're looking for changes in the enthalpy. When we're working with an incompressible substance, C sub P and C sub V are exactly the same. So the designation that we use is just C sub P, so that, again, whether it's a gas or a liquid, you know to look up the value that is C sub P. Now, this is the energy that is lost by the hot fluid. In the heat exchanger, all the heat that's lost by the hot fluid is gained by the cold fluid, and that will be defined as the mass flow rate times the specific heat times the temperature at the exit minus the temperature at the inlet, because this fluid, the cold fluid, will be increasing in temperature along the length of the heat exchanger. Now, just to go back to a couple of figures here, or to reference a figure here. So this was just for the double pipe heat exchanger. We can see here that the expressions of the temperature change for the hot fluid is that it's decreasing as it moves through the heat exchanger. The cold fluid temperature is increasing. Here, this is for a parallel flow heat exchanger. And this is for a counterflow heat exchanger, where the fluids are moving in different directions. But no matter what the heat exchanger arrangement is, that hot fluid will lose heat and the cold one will gain heat. Well, that is, and those two expressions for the change in essentially the enthalpy, the rate of change of the enthalpy of those two fluids, can be assessed just by measuring the mass flow rate and the inlet and exit temperatures for each of those individual fluids, to determine exactly how much heat is lost by one or gained by the other. But now we also want to consider, well, what is the heat transfer rate for the exchange of heat? All the heat that is lost by the hot, again, is gained by the cold fluid, but how does that actually happen? Well, when we consider a fluid flow through a pipe, or let's say just a double pipe here. So I have my hot fluid on the inside and the cold fluid on the outside. So there'll be some transfer from the hot fluid to the cold fluid. Now, as we move along the length of this heat exchanger, there's heat transfer from the hot fluid into the cold fluid all along the length of the inside surface of this pipe. But now the pipe has a thickness associated with it. So here, if I indicate the thickness of this pipe, and consider, well, how does heat get from the hot fluid into the cold fluid? Well, first there has to be convection from the hot fluid to the inner surface of the inner tube that separates the hot and cold fluids. Then we have conduction heat transfer to get from the inside surface to the outer surface of this pipe that confines the hot fluid and separates it from the cold fluid. Then we have convection that occurs from the outside surface of the pipe into the cold fluid. So there's actually a resistance that we can consider for the for the total resistance from the hot fluid eventually to the temperature of the cold fluid. So if we were to construct a resistance network, there would be three resistances here. Well, here we'd have the temperature of the hot fluid and the temperature of the cold fluid. And we would have a convection resistance on the inside, a convection resistance on the outside of this pipe, and we would also have a conduction resistance through the thickness of this pipe that separates the two fluids. So we could define, let's say, a total resistance that we just call R, but it's just a sum of these thermal resistances here, two convection resistances and a conduction resistance. Well, we know that there will be a heat transfer coefficient associated with the resistance due to convection. Recall that the resistance due to convection is just 1 over H times A. And for a circular pipe or a circular wall here that is separating these two fluids, the resistance due to conduction can be just written as a natural log of the outer diameter over the inner diameter of the pipe divided by 2 pi KL. So when we consider these two resistances by convection, that would be defined as 1 over HA, and the conduction resistance by this expression that involves a natural log of the ratio of the outer and inner diameters. We consider that this expression of R total will actually change as we move along the length of this heat exchanger. The conduction resistance will stay the same. If we have a constant cross-sectional area pipe with a constant thickness, DO and DI would be constants, and the thermal conductivity would just be the thermal conductivity of that material. But recalling from chapter 8, when we have internal flow, in this pipe, as fluid moves through the pipe, if we have a thermally developing condition in a thermal entry region, we know the heat transfer coefficient is changing as a function of position as the fluid moves along the length. Let's say the hot fluid is moving along the length. This heat transfer coefficient will be changing until we get to a thermally fully developed condition. So this expression of the resistance due to convection, if the heat transfer coefficient approaches infinity at the very beginning of the pipe and gets smaller, it says that this resistance due to convection is going to increase as we move along the length until H becomes a constant. And we didn't cover annular flow, but the cold fluid is also moving through a confined tube, and it will have a thermal intra-region length and eventually get to a thermally fully developed condition. So its heat transfer coefficient will be also changing as a function of position. So as we move along the length of this heat exchanger, the resistances due to convection will be changing. And so this gives us reason to define another expression, or actually redefine another expression that was first presented in chapter 3 of what's called an overall heat transfer coefficient, where the overall heat transfer coefficient, U, is used to define a combination of thermal resistances, or is based on a definition of multiple thermal resistances that have an overall heat transfer coefficient such that in a problem like a heat exchanger problem, it will be representative of the combination or the sum of all these resistances, these two convection resistances and this conduction resistance. So that if we consider the heat transfer rate as delta T divided by the resistance, we can write an overall heat transfer coefficient times the surface area times a delta T can be defined so that the overall heat transfer coefficient would be an average value of this resistance, this total resistance, as we move along the entire length through the heat exchanger, so that this overall heat transfer coefficient has the same units as the convective heat transfer coefficient, which is watts per meter square Kelvin, but is representative of this average value of the resistance, or an average value of the of an expression of a convection resistance, so that this resistance, that total resistance, can be defined as delta T divided by U times, 1 over U times A sub S, so that it looks just like an expression of a resistance due to convection, except that this overall heat transfer coefficient can take into account multiple expressions of convection terms. Here we have two of them for the convection processes that will be responsible for getting energy out of the hot fluid and into the cold fluid, along with the resistance due to the conduction that would have to occur through the pipe that separates the two fluids. This expression of this overall heat transfer coefficient allows us to write an expression for the amount of heat or the heat transfer that is exchanged between the two fluids. This expression can be written as U times the surface area, and this will actually be multiplied by what we call a log mean temperature difference. And this is in your text, Ln. That log mean temperature difference was an expression that we defined when we were solving problems that had a constant surface temperature for an internal flow. So there was a pipe with a surface temperature that was constant that caused the temperature of the fluid to vary logarithmically. Well, in the expressions of these heat transfer rates that would occur between the hot and cold fluids, the temperature variation of the fluids are both nonlinear. When I go back to the expressions of those temperature profiles here for the parallel flow and for the counterflow double pipe heat exchangers, you can see here that the hot fluid, if we extended the length of this heat exchanger, eventually the hot fluid and the cold fluid, the hot fluid temperature, let's say, would keep decreasing and the cold fluid would keep increasing until they meet, and then there's no more heat exchange that would occur. But this would be a logarithmic expression for the temperature variation here. The same for the cold fluid. In the counterflow heat exchanger, the limit to the cold fluid temperature when it comes out of this heat exchanger, if we extended the length, now here they're flowing in opposite directions, but the limit for the cold fluid outlet temperature will be the hot fluid inlet temperature. The limit for the hot fluid outlet temperature will be the cold fluid inlet temperature. So here we'd also have a nonlinear expression of the temperature variation, and thus we would have to consider, well, what is the average temperature difference along the length of the heat exchanger that we can use to actually calculate a heat transfer rate that occurs between the two fluids. So when we're writing an expression for the heat transfer that occurs between both fluids, This expression of the overall heat transfer coefficient is an average value along the entire length, and the log mean temperature difference is an expression of the average temperature difference that occurs along the entire length of the heat exchanger. So the definition of that log mean temperature difference is just delta T2 minus delta T1 divided by the natural log of delta T2 over delta T1. Now, when this is applied to a double pipe heat exchanger, if it's, actually, I'm going to draw it. Actually, I'll just use the figures that we have already. So here, if I just use these two here, here this would be position number 1 and position number 2. If I wanted to calculate the log mean temperature difference for this heat exchanger, that is with the parallel flow arrangement, delta T2 here would be the hot fluid temperature, hot outlet temperature of the hot outlet temperature and the cold outlet temperature. So this would be T hot out minus T cold out here. Delta T1 will be the hot inlet temperature minus the cold inlet temperature, T hot in minus T cold in. These two temperature differences, one written for position number 1, that's a temperature difference, that's delta T number 1, and here this would be delta T number 2, so that the log mean temperature difference is just delta T2 minus delta T1 over the natural log of the ratio of delta T2 to delta T1 here. For the counterflow heat exchanger, because these temperature differences are based on positions, the definitions will change slightly. Here, I'm evaluating the two temperature differences at these positions, where this will be position number 1 and position number 2. Well, for this problem, the counterflow heat exchanger, the temperature difference at position number 1, delta T1, would be the hot inlet temperature minus the cold outlet temperature. Delta T2 will be the hot outlet temperature minus the cold inlet temperature. So the temperature differences at those two positions for the heat exchanger are defined differently, because in one, the fluids are in the counterflow, they're flowing in opposite directions. In the parallel flow heat exchanger, they're flowing in the same direction. The log mean temperature difference will still be defined exactly the same way. It's just that the temperature differences are defined in a different way. So here, this counterflow heat exchanger, again, is going to give you expressions of the greatest average temperature difference that occurs along the length of the heat exchanger when we're considering, or let's say the greater, since there are just two considerations for a double pipe heat exchanger. You'll get, for the same inlet and outlet temperatures for the hot and the cold fluids, you'll get a higher average temperature difference for the counterflow heat exchanger compared to the when comparing the counterflow and the parallel flow heat exchangers. Now, this value that is the overall heat transfer coefficient, U, actually, I want to just refer here, because U, this value here, because we do have to consider that in a heat exchanger, depending on the type of heat exchanger is, the heat transfer coefficient, let's say for the fluid that is moving through a tube, is a function. So let's say, just to consider the simplest configuration, which is the double pipe. When that hot fluid is moving through the heat exchanger, the higher the flow rate, the closer we can transit. We can have a laminar flow condition, or we can have a turbulent flow condition, let's say on the inside pipe or even the outside pipe. Well, we know that the velocity of the fluid is going to affect the length of the thermal entry region. So let's say if it's a turbulent flow, we would consider that the thermal entry region length would be approximately the same as the hydrodynamic entry region length, which would just be 10 times the diameter of the pipe. And then the heat transfer coefficient will be considered to be a constant. If it's a laminar flow, the thermal entry region length is 0.05 times the diameter times the Reynolds number times the Prandtl number. And if we change the velocity of the fluid, the length of that thermal entry region length along the pipe will change. And so if the heat transfer coefficient for one of the fluids is changing, the overall heat transfer coefficient would also, that's going to affect the value of the overall heat transfer coefficient. So if I transition from a double pipe heat exchanger to a cross flow heat exchanger or shell and tube heat exchanger, those expressions of how the heat transfer coefficient for one or both of the fluids changes as a function of position can vary greatly. So here in table 11.1, there are just ranges of the values of the overall heat transfer coefficient without a consideration for the type of heat exchanger that it is. Here says type, but when I say type, I'm meaning double pipe, cross flow, or shell and tube heat exchanger. Here they're just talking about the two fluids that would be moving through that heat exchanger and what the range of typical values are for the overall heat transfer coefficient. Again, taking into account that 1 over U times the surface area will be defined as that total resistance, and that total resistance will at minimum consist of two convection resistances, one on the inside, one on the outside of the pipe, and a thermal resistance due to conduction. And that's not taking into account any fouling that might occur. Well, fouling is just a development of some oxidation that occurs on the inside, outside, or both the inside and outside of the pipe, which would just be additional conduction resistances. But that overall heat transfer coefficient U is used to define an expression of a total resistance that takes into account, again, at minimum, these three resistances. You could add two more conduction resistances if there's oxidation that occurs on the inside of the pipe and on the outside of the pipe. And that's very typical, particularly if you're using water as or water as the hot and the cold fluid. But these are just typical values that you might find, but these values of the overall heat transfer coefficient are empirically determined, because I can have a heat exchanger of a particular arrangement, and if I change the velocity of the fluids moving through it, I'm going to change the heat transfer coefficient and thus change the overall heat transfer coefficient. If I have an aluminum alloy or a copper alloy, or maybe some mild steel or type stainless steel, and I make it really thin, well, I'll get different values for the conduction resistance. So, and that conduction resistance is also a part of the determination of this overall heat transfer coefficient. So these values presented in table 11.1 are just ranges of values that can apply to both or apply to all types of heat exchangers that include both of these particular fluids that are used as the hot and cold fluids in those heat exchangers. So notice here that for water to air in fin tubes where the water is in the tubes, these are relatively low values of the heat transfer coefficients when the expressions of the heat transfer coefficients are based on here, these designations here. This is based on this first one here. It looks like a kind of looks like a little cross, but if you look at it really closely, it's not really. But this this value of 30 to 60 watts per meter squared Kelvin, when it says that water is flowing in the tubes, it gives you two ranges, 30 to 60 and 400 to 850. This is based on the air side surface area, which is the larger of the two surface areas. If this is a finned tube, this is like the cross flow heat exchanger, and the area on the outside of the tube is greater than the area on the inside of the tube. And recall that if these are finned, there's much more area available for the air that's on the outside of the fin than the water that's on the inside of the tubes. So if you base the overall heat transfer coefficient on that surface area that the air is exposed to, you get much lower heat transfer coefficients than if you base it on the area on the inside of the tube. This double, I'll call it cross, this double cross is the same heat transfer rate, but it's based on the surface area on the inside. And recall that the overall heat transfer coefficient is watts per meter squared Kelvin. So if I have a much smaller area over which I'm distributing that heat transfer rate, I'll get a larger heat transfer coefficient. So for both the water to air in a tube and steam to air, here this is just steam moving through the tubes. You see that when the area is the inside area in the pipe, you get much higher overall heat transfer coefficients. And that's fine. It's just a matter of making sure that the that the finned area, this is the only the finned area on the outside of the tubes is included here, because many times we are considering finned surfaces for cross-flow heat exchangers. So that if we're defining an overall heat transfer coefficient, it's important that you make note of which area that overall heat transfer coefficient is being calculated for. Now, the expressions that we use, going back to the heat transfer rates, these heat transfer rates, this is the heat out of the hot fluid, the heat into the cold fluid. All three of these expressions have the same magnitude. Q dot hot, Q dot cold, and Q dot exchange are all going to be exactly the same. We can always measure the amount of heat lost or gained by the cold fluid by just measuring the mass flow rate and the temperature difference that it experiences through that heat exchanger. But in order to define an overall heat transfer coefficient, we'd use one of these heat transfer rates to equate it to the expression of the heat exchanged, measure the surface area that is inside of a given heat exchanger, and calculate the log mean temperature difference based on the measured temperatures for the inlet and exit temperatures for both the hot and cold fluids. And that allows us to find the overall heat transfer coefficient. So if this expression is just rearranged, those ranges of overall heat transfer coefficients in table 11 just come from an expression that says that U is the heat transfer rate divided by the surface area times the log mean temperature difference. Where again, the log mean temperature difference, if I have a given heat exchanger, I just need to measure the inlet and exit temperatures for both fluids. From the geometry of the heat exchanger, calculate this surface area, and this heat transfer rate can just be calculated as taking the temperature difference for one of the fluids with its mass flow rate and specific heat, and determining, well, how much heat entered the cold fluid or how much heat entered the hot fluid, because that is exactly the amount of heat that was exchanged. And I can calculate the overall heat transfer coefficient for that heat exchanger under those particular flow conditions with those two fluids. So that's how that range of expressions in table 11-1 are actually derived. As you set the two fluids with their known specific heats, you measure the temperatures and the surface area that is exposed on the inside and the outside of those surface areas. where heat exchange is going to occur out of the hot fluid and into the cold fluid. And you can calculate exactly what this value of the overall heat transfer coefficient to establish those ranges. But now, how do we use those values? Or during a heat transfer analysis? Well, we use them in two different methods, or with two different methods for providing an analysis of a heat exchanger. These two analysis methods applied to heat exchangers are what we call the effectiveness NTU method and the log mean temperature difference method. Log mean temperature difference method. Now, in each of these, we still will always use the expression of a heat transfer rate being defined in terms of the cold fluid. Here, the cold fluid will be the mass flow rate times the specific heat. It's going to say T cold out minus T cold in. The heat transfer rate out of the hot fluid is the mass flow rate times the specific heat times T cold, T hot in minus T hot out here. That heat exchange is defined just based on this mass flow rate times the specific heat. This expression we call a m dot C sub P. We'll use a capital C, and this is what's called the capacity rate for the fluid. And that value that is the capacity rate is a quantity that we'll use for some of the analyses. We consider, well, what are the units for the capacity rate? A mass flow rate is kilograms per second. A specific heat is joules per kilogram Kelvin. So here the kilograms will cancel. Joules per second is watts. So this is just watts per Kelvin or watts per degree C. That is what the units are for a capacity rate. And often this expression, you may see this as Q dot cold is equal to C times T sub CO minus T sub Ci. And we'll usually write this as C sub C. This is the capacity rate of the cold fluid. And for the hot fluid, this will be the capacity rate of the hot fluid, C sub H times T hot in minus T hot out. So just you can write the expression in terms of the product of the mass flow rate and the specific heat, or the capacity rate, which is just the product of those two expressions. But we'll be comparing these capacity rates later, and thus it's convenient to go ahead and define what the capacity rate actually is. Now, when we're writing these expressions, all we're defining is the amount of heat gained by the cold fluid and the amount of heat lost by the hot fluid. Now, these two methods for solving or analyzing heat exchangers, the effectiveness NTU and the log mean temperature difference method, are just different methods for describing how the heat is transferred between the hot and cold fluids. Now, the log mean temperature difference method is the easier of the two to apply. Well, I guess kind of depends on your perspective, but it's as far as like a double pipe heat exchanger, the log mean temperature difference method is easier. The log mean temperature difference method just says that we define the heat transfer rate as that overall heat transfer coefficient times the surface area times the log mean temperature difference. So that for a heat exchanger that is a double pipe heat exchanger, the expression of the, so if I have the pipe here, well, I think this is a little easier just to draw this way here. So if I have fluid moving into the inner pipe. Let's say I have the hot fluid moving through the inner pipe and the cold fluid moving through the outer pipe here. Here we have a position number 1 and position 2 for the heat exchanger. The two fluids will move through the heat exchanger so that along the length from position 1 to position number 2, the hot fluid will decrease in temperature, the cold fluid will increase in temperature. So these expressions for the heat transferred out of the hot fluid is just going to be based on the mass flow rate of the hot fluid and the temperature difference that it experiences. For the cold fluid, the mass flow rate of the cold fluid times the specific heat of the cold fluid times the temperature difference that it experiences. Now, if you have a problem where the specific heat is not specified in the problem statement, the specific heat, C sub P, is evaluated at the average temperature of the fluid. So this is just, let's say if it's the hot fluid, it will be T hot in plus T hot out divided by 2. And this is usually called the bulk temperature of the fluid. So let's say you were given water and the temperature difference that it experienced between this inlet and outlet, or let's say the temperatures were 20 degrees at the inlet and 10 degrees at the outlet. That just says we would evaluate the specific heat at 15 degrees, 10 plus 20 divided by 2, and that will be the temperature at which we would get the specific heat for that fluid. In many of the problems, they'll tell you to evaluate or use a specific value of the specific heat in order to calculate, let's say, the heat transferred out of the hot fluid. But if it's not given, that temperature that at which we would evaluate is just the average temperature between the inlet and outlet for that particular fluid. But by this log mean temperature difference method, this heat exchange between the two fluids is, it does take into account the inlet and outlet temperatures for the hot and cold fluids through the definition of the log mean temperature difference. This surface area is just the surface area that for the exchange between the two fluids. Now, the surface areas are based on the inner and the outer diameters of the pipe. Now, this is a heat exchanger, and so this pipe, this inner pipe, is typically made as thick as possible. So many times it's less than a millimeter thick, so that the inner diameter and the outer diameter yield essentially very small differences between the surface areas. And so for a double pipe heat exchanger, because there's only this surface or this pipe that has an inner and outer surface that essentially have the same areas, there's only one expression for the overall heat transfer coefficient that we would calculate. So in these kinds of problems, they'll often only give you the inside diameter or the outside diameter of the pipe, because the thickness is so small that the inner and outer areas are essentially the same value. But that surface area would just be defined based on that diameter that is given. And an overall heat transfer coefficient, if it's specified in a problem, can be used to calculate the heat transfer rate. Or if we've taken the heat transfer rate from the hot or the cold fluid, we can solve for the overall heat transfer coefficient. But here is just a matter of determining or using this expression for the heat exchange between the two fluids to answer other questions that might be associated with it. Now, this expression for the log mean temperature difference, that would the application of the log mean temperature difference method is applicable directly for double pipe heat exchangers. And the reason for that is this: recall that the log mean temperature difference, delta T ln, is delta T2 minus delta T1 over the natural log of delta T2 over delta T1. Now this is the temperature difference here. This will be delta T at position 1, and this is delta T at position number 2. And that's because we can define these in the double pipe heat exchanger that's parallel flow. The inlet position is the inlet the inlet position for both the hot and cold fluid is the same position in the heat exchanger, and the outlet for the hot and cold fluids are both at the same position, number 2 here. And so we can use this expression directly for the calculation of the log mean temperature difference. The same can be applied when we consider a counterflow double pipe heat exchanger. Here, let's say we have the hot fluid coming in here and the cold fluid coming in here. Well, there's still a position number 1 and position number 2. For the parallel flow heat exchanger, delta T1 is just the hot inlet minus the cold inlet. Delta T number 2 here, delta T number 1 is the hot inlet minus the cold inlet. Delta T number 2 is the hot outlet minus the cold outlet. In the counterflow heat exchanger, that is the double pipe, here the hot fluid comes in and decreases in temperature, and the cold fluid temperature increases. So here, when we define delta T1, again, this is the hot inlet minus the cold outlet, and delta T2 is the hot outlet minus the cold inlet. And so this expression for the log mean temperature difference, where again, this log mean temperature, this expression for the heat transfer rate using the log mean temperature difference method uses a log mean temperature difference as an expression of the average temperature difference along the length of the heat exchanger times the surface area times the overall heat transfer coefficient to get a heat transfer rate. Now, this expression does not directly apply to the shell and tube and the cross-flow heat exchangers, and the reasons for that is that the hot and cold fluids do not share inlet and exit or inlet and outlet positions. When we look at these figures for the heat exchangers, again, we have for the parallel flow, both fluids come in at this position, both leave at this position. One hot fluid comes in here and leaves on the other end. Cold fluid comes in here and leaves on its other end. So the positions 1 and 2 are shared positions on the heat exchanger itself. But when we get to the cross-flow heat exchanger, based on the arrows that are drawn here, if let's say the fluid moving through the tubes is the hot fluid, well, that says that the hot fluid comes in at the back of this figure, and the hot fluid would leave at the front. The cold fluid, if it's the air that's moving through the fins, is coming in from the left and leaving on the right. So they don't share a position where they come in and go out of the heat exchanger. The same would be considered for the one fluid mixed and one unmixed in this cross-flow heat exchanger. The fluid in the tubes comes in from the back side and comes out of the front here. The gas comes in from the left and leaves on the right. So they don't have shared positions. Of course, they share positions within the heat exchanger as they're exchanging heat, but the inlet and the outlet positions are not shared at all. And the same would be true for the shell and tube heat exchangers. The fluid that's moving through the shell here in and out, and through the tubes in and out, they don't share the same position. So we can still use the log mean temperature difference method to write the expressions that we would use to solve these problems. But for these two heat exchangers, when we use the log mean temperature difference method, let's say for the shell and tube, and the cross flow heat exchangers. Again, the same expressions of the heat transfer out of the hot fluid is still the capacity rate of the hot fluid times T hot in minus T hot out. And the heat transferred into the cold fluid is still the capacity rate of the cold fluid times T cold out minus T cold in. That never changes no matter what the heat exchanger arrangement is. But for the heat exchange between these two fluids, here the heat exchange will just be the overall heat transfer coefficient, the surface area, times a log mean temperature difference, times a correction factor. And that correction factor is based on the geometry of the problem, because when we calculate this log mean temperature difference, the log mean temperature difference will be based on inlet and outlet temperatures for the hot and cold fluids. But recall that they don't share the same position in the shell and tube and the cross flow heat exchangers. So this correction factor is required, and that correction factor requires a use of figures in order to get the value of the correction factor to be applied to this equation that is the heat transfer that is exchanged between the two fluids. These two expressions of the heat lost by the hot and the cold don't change. So when we look here at the figures that are provided for this log mean temperature difference method, here we have these expressions. Now, this is the correction factor on the y-axis, and this is for all four of these figures. On the x-axis is this value that is P, and that's the same on all four figures, and the lines, the colored lines that are drawn, are for this value that is R, where the definitions of these quantities are given. P is, for all of these expressions, is T2 minus T1 over capital T1 minus T1. Now, what are those temperatures? Well, all of these are temperatures, but there are uppercase and lowercase that are used. All of them are temperatures. Capital T1 and capital T2 refer to the temperatures of the fluid moving through the shell. This is a representative of a shell and tube heat exchanger. Here's another shell and tube heat exchanger. This is a single shell pass, two tube pass shell and tube heat exchanger. This is a two shell pass, four tube pass heat exchanger. But the value that is P is just based on those temperatures. 1 and 2 indicate 1 is an inlet, 2 is an outlet. So here T1 is the capital T1 is the shell inlet temperature, capital 2 is the shell outlet temperature. Lowercase t1 is the tube inlet temperature, lowercase t2 is a tube outlet temperature. So this ratio that is P is on the x-axis. The ratio that is R is capital T1 minus capital T2 over T2 minus T1. So here, this is the temperature difference between the inlet and the outlet of the shell side pan, or the fluid moving through the shell, and T2 minus T1 is the temperature difference between the two fluids that, or the fluid that is passing through the tube. Now, for the same definitions are used. So that here I'm going to write lowercase t is the tube fluid temperature, and uppercase t is the shell fluid temperature. When we consider the cross flow heat exchanger, so that we can use the expression of that corrected expression for the log mean temperature difference, method. Here, it's harder to see with this one because this is both fluids unmixed here. But on the one where one fluid is mixed and the other is unmixed, the lowercase t refers to the cross flow fluid, and uppercase T. No, actually, I'm sorry. Let me make sure I get that correct. No, the lowercase, this should be the tube fluid. And uppercase T is the cross flow fluid here. So that the temperature of the fluid that's moving through the tubes, typically that's the liquid, is going to move through the inner surface. And on the outside surfaces where we have the fins, where we have the outside surface of the tube, is the cross flow fluid. But these ratios would have to be calculated, P and R, in order to find the correction factor. So we have the temperatures for the inlet and outlet of the cross flow heat exchanger or the tube, shell and tube heat exchanger. We can calculate these ratios that are P and R and look for the intersection of the value that you calculate for P and the value that you calculate for R, and look for that intersection point to then get the value for the correction factor. Where again, that correction factor is just use UA times the log mean temperature difference times F. So the log mean temperature difference is still going to be based on T1, the hot fluid and the cold fluid inlet and outlet temperatures. So that here, let's say, just considering this cross flow or this cross flow heat exchanger where both fluids are unmixed, we have, still have two outlet temperatures and you have two inlet temperatures, but the delta T's for the log mean temperature difference are based on a consideration of the fluids flowing like they were flowing through a counterflow double pipe heat exchanger. So I'm going to write for this problem, if this is delta T2 minus delta T1 over the natural log of delta T2 over delta T1, whenever we're writing this expression with the correction factor, we calculate the log mean temperature difference based on a counterflow double pipe heat exchanger. So all that is a consideration of, we imagine that on a TX diagram where we have 2 and 1, all that means is that we consider that the two fluids flow in opposite directions to one another. So there will be a temperature decrease of the hot fluid and a temperature increase of the cold fluid as they flow in opposite directions, is how we calculate that log mean temperature difference. So that says that the hot outlet temperature minus the cold inlet temperature will be the delta T2 for the log mean temperature difference calculation. And delta T1 will be the hot inlet temperature minus the cold outlet temperature. Again, we have two outlet temperatures, lowercase T2 and uppercase T2. We have two inlet temperatures, uppercase T1 and lowercase T1. So depending on which is the hot fluid and which is the cold fluid, we would just calculate the log mean temperature difference, assuming a flow configuration for the calculation of the log mean temperature difference that would be like a counterflow heat exchanger that is that will be a double pipe configuration. So we can use the log mean temperature difference. We just have to modify the definition of the log mean temperature difference calculation, because those positions at which the fluids come into and go out of the heat exchanger are just different. They don't share common positions along the length of the heat exchanger. They come in at different positions and they go out at different positions. So in order to use these correction factors, that this is how we would calculate that log mean temperature difference for a given problem. So let's look, before I go to the effectiveness NTU method, which is just a different method for calculating the same quantities. Here we'll consider a problem that we can solve using these figures. And these figures are actually, let me see what the figure numbers are here. This should be like figure 1119 in your text here. I think they have letters designated with them, but this is (11-19) here for reference. But these expressions that we use are required if we're going to use the log mean temperature difference method to actually solve for any, well, not necessarily heat transfer rate, because we can calculate heat transfer rates directly from the properties associated with one of the fluids. But if we want to calculate, let's say, the overall heat transfer coefficient or the required surface area for a given heat transfer coefficient, then we would write those expressions and apply them for the particular type of heat exchanger that we're considering. So let's look at here at a cross flow heat exchanger. So this is like the automobile radiator, or it could be like the heat exchangers that are the evaporator and condenser in a air conditioning system. So here we'll consider a cross flow heat exchanger where both fluids are unmixed. So what does that mean? That means that we have fluid moving through the tubes with fins that keep the fluid that is typically the gas on the outside. Well, I'll just say the fluid to keep it general. The fluid that's on the outside of the tubes has confined spaces through which it would move. So look at the figures for those cross flow heat exchangers. We have two, again, both fluids unmixed. The fluid in the tubes is always unmixed. But if we have fins that confine the flow path for the fluid that's moving on the outside, the cross flow fluid, then that's both fluids unmixed. If we don't have fins, then the cross flow fluid is considered to be mixed in that it can move around throughout the volume that makes up the heat exchanger. So here we're considering a problem that looks like this. This is why I said it looks like, or it would be like, an automobile radiator. In this problem, we're going to consider that the two fluids moving through the heat exchanger are water and oil. And here, this water and oil, so this is not exactly like your automobile radiator, but this would just be two liquids moving through a cross flow heat exchanger, so that one of them is moving through the tubes and the other is moving through, or is the cross flow that's moving over the tubes. Here we'll consider that the oil is the cross flow fluid and the water is the tube fluid. And here the water enters at 16 degrees C and exits at 33 degrees C. And the oil, here this enters at 38 degrees and exits at 29 degrees C. So here, we can tell which one is the hot fluid and which is the cold fluid. The one that is decreasing in temperature is the hot fluid. So the oil, here, this is the hot fluid, and this one is the cold fluid. The cold fluid is entering and exiting at a higher temperature. So, so we can tell immediately which is the hot and cold. And here we'll consider that the specific heats, the specific heat of the oil is going to be specified here. So when we consider an expression for, let's see, for the hot fluid, the specific heat hot fluid is given as 1,930 joules per kilogram Kelvin for the specific heat, and its density is 870 kilograms per cubic meter. And we'll consider that the oil is flowing at a rate of 0.1, the volumetric flow rate here is 0.19 cubic meters per minute. So I'll just draw well, actually, I'm going to just draw schematically just. Oops. So I'll consider that I have tubes running through the heating. No, I don't want to draw it that way. I'll just draw here. Here we have the cross flow and the tube flow, where we consider that the tubes will be coming in from the back side and coming out the front side, like the schematic that are considered, and the cross flow is moving through the fins from left to right here. And I'm just drawing this so we can put these temperatures on here on the figure. So if the water is the tube fluid and enters at 16 degrees, so here I draw 16 degrees here on the back side, 33 degrees on the front, and the cross flow, which is the oil, comes in at 38 degrees and leaves at 29 degrees. So again, they don't have a shared a position for entering and exiting the heat exchanger. We have back to front and left to right here. Now we'll consider that the surface area for the heat exchanger is 20 square meters here. And that would be for the air, and not the air side, but for the cross flow. Because if this is an unmixed or a cross flow heat exchanger where both fluids are unmixed, the fluid moving through the tubes has a surface area that's just the inside surface area of the tubes. For the cross flow, it will be the surface area where heat transfer is occurring is the outside of the tubes and all of the surface area for the fins that are attached to the tubes. So here, this surface area of 20 square meters, I'm specifying that that's for the cross flow. That's where the heat exchange is occurring for that fluid that's flowing on the outside of the tubes. And here we want to determine the overall heat transfer coefficient. That is U. Now, when we're considering the content or the what is given in the problem, some things that we know. The heat transfer out of the hot fluid is the capacity rate of the hot fluid times T hot in minus T hot out. The heat transfer rate into the cold fluid is the capacity rate of the cold fluid times T cold out minus T cold in here. So when I'm writing these, writing those expressions, then this allows me to consider, well, first, well, what is the heat transfer rate? Because these two heat transfer rates are also going to be equal to the heat transfer rate that is exchanged between the two fluids. And since this is a cross-flow heat exchanger, this would be the overall heat transfer coefficient times the surface area times the log mean temperature difference times its correction factor. Because it's a cross-flow heat exchanger, that heat exchange requires that we calculate the correction factor for a cross-flow heat exchanger where both fluids are unmixed. Now, we have the inlet and outlet temperatures for both the hot and the hot fluid and the cold fluid. The capacity rate for the just the capacity rate is just defined as the mass flow rate times the specific heat. Well, we're only given the temperatures of the water at its inlet and exit. But for the oil, we're given the specific heat, and we're given the density along with the volumetric flow rate here. Well, the volumetric flow rate multiplied by the density will give us a mass flow rate. So we can calculate that for the hot fluid, because the mass flow rate is just the density times the volumetric flow rate, and multiplied by the specific heat will give us the capacity rate for the hot fluid. And we have the two temperatures for the hot fluid. So if all the heat lost by the hot fluid is gained by the cold fluid, we could actually calculate the capacity rate for the cold fluid, because we have the cold outlet and inlet temperatures, and that heat gained by the cold is exactly the amount of heat lost by the hot fluid. So this would allow us to find the capacity rate of the cold fluid, in that it would just be Q dot cold over T cold out minus T cold in. So that's not asked for in this problem, but we could find it. And if a mass flow rate was given, or if we evaluated the specific heat at the average temperature between the inlet and outlet of the cold fluid, we could find exactly what the mass flow rate must be for a given value of the specific heat evaluated at the average temperature between these two. But that's not required in this problem. We're looking for the overall heat transfer coefficient. If the amount of heat exchanged by the two fluids is equal to the amount of heat lost by the hot fluid, then we have that quantity. We're given the surface area. We can calculate the log mean temperature difference because we're given all of the temperatures, and we would have to calculate the correction factor and use figure 1119. But this would allow us to solve for U, so that U would just be the heat transfer rate divided by the surface area times the log mean temperature difference times that correction factor. So we can get to this expression just by proceeding through the calculations that I outlined here. So the first thing we need to find is the mass flow rate, which is just the product of the density and the volumetric flow rate here. So if the mass flow rate m dot is rho times v dot, then the density here is 870 kilograms per cubic meter, and the volumetric flow rate is 0.19 cubic meters per minute, and there are 60 seconds in a minute. So we can get a mass flow rate here. So here we've got 0.19 times 870 divided by 60. All right, so this is 2.755 kilograms per second for the mass flow rate. So the capacity rate is just that mass flow rate times the specific heat. So Q dot for the hot fluid is the capacity rate of the hot fluid. So this is 2.755 kilograms per second times the specific heat of 1,930 joules per kilogram Kelvin times the temperature difference experienced by the hot fluid. Again, the hot fluid is the oil. So the hot inlet of 38 degrees minus the hot outlet of 29 degrees. Again, this temperature difference in degrees C is the same as the temperature difference in Kelvin. So degrees C and Kelvin will cancel. Kilograms cancel. So I'm left with joules per second. So this will be some number of watts that is the heat transfer rate out of the hot fluid. So here times 1930 times 9. All right, so I get here an expression of the heat transfer rate that is 47,854.4 watts. So that's the amount of heat lost by the hot fluid. But this is also the amount of heat gained by the cold fluid. And this is also the amount of heat that is transferred between the two fluids. So in determination of the overall heat transfer coefficient, now we have this heat transfer rate that is in the numerator. We have the surface area. Now we need to look at, well, what is the log mean temperature difference? Well, the log mean temperature difference, again, is delta T2 minus delta T1 over the natural log of delta T2 over delta T1. Now here, delta T2, if this is like a cross-flow heat, a counterflow double pipe heat exchanger, this will be the hot outlet temperature minus the cold inlet temperature, and delta T1 will be the hot outlet temperature, hot inlet minus the cold outlet. Now here I'm going to go ahead and just draw what for a double pipe counterflow heat exchanger will look like again. The hot inlet, if I'm saying, comes in at 1 and leaves at 2, and the cold inlet comes in at 2 and leaves at 1. Draw that with a little more variation here. So here the hot inlet is at position number 1, and the cold outlet is at position number 1. So delta T at position 1 will be hot inlet minus cold outlet. At position number 2, this will be the hot outlet minus the cold inlet. So in this problem then, delta T2, the hot outlet temperature is 29 degrees, and the cold inlet is 16 degrees. So 13 degrees for delta T2, and delta T1 is the hot inlet of 38 degrees minus the cold outlet. The cold outlet is 33 degrees. So here this is just 5 degrees. So now we have these temperatures, or these temperature differences, that are calculated for a double pipe heat exchanger that has a cross flow arrangement, so that now we can calculate the log mean temperature difference here. So delta T2 is 13 degrees minus delta T1 of 5 degrees divided by the natural log of 13 divided by 5 here. So this expression, 13, the natural log here of 13 divided by 5. All right, so I get a log mean temperature difference that is 8.3725. And that's degrees C. That's the average temperature difference, an expression of the average temperature difference that exists along the length of the heat exchanger. So now I have that value. And now we need to find the correction factor. Now the correction factor is going to come from the definition of the definition of the quantity from the charts here. So here we have both fluids unmixed in the cross-flow heat exchanger. So in order to find the correction factor, which is on the y-axis, I need to calculate P and also R and get it from this graph here. So with the definitions of P being T2 minus T1 divided by T1 minus, or capital T1 minus T1, and R being T1 minus T2 over T2 minus T1, like this. So these expressions for the heat exchanger are the quantities that we want to consider, but then we have to consider, well, what are the temperatures? Well, T2 minus T1, well, T2 minus T1, this is the temperature difference for the fluid that is moving through the tubes here. So this is the, well, actually I'm gonna write this. The lowercase t is for the tube fluid, and uppercase T is for the cross fluid, or let's say cross flow fluid. So the tube fluid is our cold fluid, and so P then is the outlet minus the inlet of the tube. So 33 minus 16 divided by the inlet temperature for cross flow fluid, which is 38 degrees, minus T1, which is 16 here. And R is the temperature at the inlet of the cross flow fluid, which was 38, and the outlet of 29. And T2 minus T1, here's lowercase t2, 33 minus 16. So here, let's see, calculate these quantities here, 33 minus 16 and 38 minus 16. All right, so I get 0.773 for the value of P, and for R, minus 29, 33 minus 16. I get 0.529. So those are the two quantities for P and R. So now we have to look those up on the chart, on the figure here. So single pass cross flow with that both fluids unmixed. So we had 0.772 for P. So here we have 0.7, 0.8, 0.75. So I'm going to say it's about right here. And we read up to 0.529 for R. So here, yep, here you go, this green line I drew the last time here. So I'd look for this to intersect at about right here. And that is here 0.8, 0.85. So I'd say the factor is about 0.875 for the value of the correction factor. So here, so from the chart, I mean, you can find, you see that there will be some error because we're not directly on one of the green lines. We're not exactly on one of these grid lines associated with the x-axis. So these are there's no other calculation associated with these lines in the these green lines in the intersections of these. So we have to kind of eyeball it from the graph, but I'd say this is about 0.8, about 0.875. So from figure 11-19, F, I'll just say is equal to 0.875 here. So with that correction factor now being defined for the log mean temperature difference method, we can calculate the overall heat transfer coefficient. So the heat transfer rate was 47,854.4 watts. The surface area was 20 square meters. The log mean temperature difference, 8.3725, and the correction factor is 0.875. So with these units, I should get watts per square meter Kelvin for the overall heat transfer coefficient. So let me go back up here to my, right there's the heat transfer rate divided by 20 times 8.3725 times 0.875 here. So this overall heat transfer coefficient is 326.61 watts per meter squared Kelvin. So that would be the overall heat transfer coefficient associated with this flow through the heat exchanger. Now, if we changed, let's say, the mass flow rate or the velocity of either one of these fluids, it would affect, again, the average heat transfer coefficient and thus the average overall heat transfer coefficient. And the way that that will be reflected is through an expression of the change in the actual heat transfer rate. And we would also expect that there would be a difference in the value of the log mean temperature difference because the delta T's would change. And thus the value that we would read as a correction factor would slightly change because P and R are based on those temperatures. Now, just to go back a little bit, I answered the actual question here, but if we want to determine, well, what is the capacity rate of the cold fluid? Because we were given information about the hot fluid to get its capacity rate. Q dot, the capacity rate for the cold fluid would be the heat transfer rate into the cold fluid divided by T cold out minus T cold in. Where our heat transfer rate out of the hot fluid, we already calculated, is the given density for the hot. We just used the density for the hot fluid. I wrote it right under the expression of the properties for the oil, and then I used it to calculate the mass flow rate for the oil to get the capacity rate for the oil. So yeah, it applies to the oil, which was the hot fluid that decreased in temperature through the heat exchanger there. So if we want to calculate the capacity rate of the cold fluid, it's the same heat transfer rate that was out of the hot fluid, 47,854.4 watts. The cold outlet temperature, that's the one that increased in temperature, so 33 minus 16. So this will give us the capacity rate for the cold fluid. So here, 47,000 here divided by 33 minus 16. So here the capacity rate is 2,814.96. This would be watts per, this could be watts per Kelvin or watts per degree C because it's based on a temperature difference. And so here, this expression is just the capacity rate, which is the same as the mass flow rate times the specific heat here of the cold fluid. Now, because we weren't given any density, volumetric flow rate, anything about that, all we know is that the product of the mass flow rate and the specific heat is 2,814.96. But now we could assess the specific heat of the cold fluid. We know the specific heat, well, we know the cold fluid is water. And here the average temperature, 33 plus 16 is almost 50 divided by 2. So this is about 25 degrees. So for water, let's say at 25 degrees C, we can look up, well, what is the specific heat of water? So if I go back to the tables, saturated water, 25 degrees, the specific heat is 4,180 joules per kilogram Kelvin. 4,180 joules per kilogram Kelvin. And so since the capacity rate, C sub C, is the mass flow rate times C sub P, then this allows me to write that the mass flow rate for the water would just be the capacity rate divided by C sub P. So if the capacity rate that we calculated of 2,814.96 watts per Kelvin divided by 4,180 joules per kilogram Kelvin, this will give us a mass flow rate that is just kilograms per second. And so if we divide that capacity rate by the specific heat of 4,180 joules per kilogram Kelvin, we get 0.673 kilograms per second will be the mass flow rate for the water, while the mass flow rate for the oil was 2.755 kilograms per second. And the difference is due to the delta T difference and the capacity rate differences that that exist for the two fluids here. Wasn't 4,000 Q hot. Angel, the heat transfer rate out of the hot fluid is exactly the heat transfer rate into the cold fluid is exactly the heat transfer rate exchanged between the two fluids. So when we're calculating these quantities, this is conservation of energy. This is the concept that when I first started talking about heat exchangers, we consider that all of the heat lost by the hot fluid is gained by the cold fluid. No other heat is lost or gained in the heat exchanger. So this is the reason that we can equate these two quantities. And that's something you're going to have to remember when you're doing a heat transfer analysis on a heat exchanger, because otherwise there will be unknown quantities that you would not be able to solve for. So that's how we would use the log mean temperature difference method for these calculations. Now, again, if you have a pipe heat exchanger, whether it be counterflow or parallel flow, again, these two expressions of the heat lost by the hot and gained by the cold are exactly the same. But if it's a double pipe heat exchanger, the correction factor is just a 1. So it's just the overall heat transfer coefficient times the surface area times the log mean temperature difference. And the correction factor would be a 1 because the two positions, position 1 and 2, are shared positions in a double pipe heat exchanger, as I drew here before. Position 1, position 2, position 1, position 2. Whether it's a parallel flow heat exchanger where the hot fluid and the cold fluid eventually come to the same temperature, or the counterflow heat exchanger where the hot or the cold outlet temperature will approach the hot inlet temperature and the hot outlet temperature will approach the cold inlet temperature. For both of those, you can just use the heat transfer rate is equal to the overall heat transfer coefficient times the surface area times the log mean temperature difference. So essentially the correction factor is just a 1, so you can use the same expression. Now, this method works very well when you just have the 3 equations here for a double pipe heat exchanger, where all you need is the heat gained by the cold fluid, the heat lost by the hot fluid, the heat exchange between the two fluids. This is these are very easy calculations to make when it's a double pipe heat exchanger. It's a little bit more complexity is added when it's a cross flow or a shell and tube heat exchanger, because it requires that you find the value that is F, the correction factor, so that you can use the log mean temperature difference method with that shell and tube or cross flow heat exchanger. But just finding F is just an additional step using the charts and pulling the value of F directly from figure 1119. But now another method for making this determination or doing a heat transfer analysis is using what is called the effectiveness NTU method. Now, the effectiveness NTU method is just a different way of calculating the heat exchange between the two fluids. So effectiveness NTU method. And here, the effectiveness and the number of transfer units are two quantities that are defined for the use of this particular method. The effectiveness here is defined as the heat transfer rate that is the heat that's either lost by the hot fluid, which is gained by the cold fluid, and exchanged between the two fluids, divided by Q dot max. Well, this is the maximum possible heat transfer rate. The maximum heat transfer rate, Q dot max, is the capacity rate that is the minimum of the two capacity rates of the fluids times T hot N minus T cold N. This will be representative of the greatest heat transfer you could have to occur between those two fluids. So C min is just the lower of the two fluid capacity rates. So, there's a capacity rate for the hot fluid, and a capacity rate of the cold fluid is the mass flow rate times the specific heat. In the previous problem, where we calculated the capacity rate of 2,814.96 for the cold fluid, and for the hot fluid, I didn't explicitly calculate it, but the capacity rate of the cold or the hot fluid will be the 2.755 kilograms per second times 1930 joules per kilogram Kelvin. Whichever is the lower of those two would be the minimum capacity rate. The hot inlet and cold inlet temperatures are an expression, or the difference between the two is the largest temperature difference that exists in the heat exchanger. And that's what we would call Q dot max. So that the effectiveness for the heat exchanger is just the actual heat transfer rate divided by Q dot max here. Now, the other term that is defined here is NTU. And NTU is short for number of transfer units. And it's an expression that is a unitless quantity, but it is defined as the overall heat transfer coefficient times the surface area divided by the minimum capacity rate. So this expression will be used in the calculations of different quantities that are a function, or different quantities that are used to define expressions that we'll use depending on the type of heat exchanger that it actually is. Now, for a shorthand, there's a lowercase c that's defined. It's not a specific heat. This is just a ratio of the capacity rates, the minimum capacity rate divided by the maximum capacity rate. Now, this value will always be 1 or less than 1. If the two capacity rates are exactly the same, you'll get C is equal to 1. But this is a ratio of the minimum capacity rate to the maximum capacity rate. So there's only two capacity rates. There's a capacity rate of the hot fluid and of the cold fluid. The lower of the two is C min. The higher of the two is C max. So we define this expression. This is what's called the capacity rate ratio. And this is just used, this is defined just for convenience, because this lowercase c will show up in some of the equations that we will reference for use of the effectiveness NTU method, such that the expressions of the effectiveness, this is a function I mean, it's defined as Q dot, the actual heat transfer rate divided by Q max. But this expression of the effectiveness is a function of the number of transfer units and the capacity rate ratio. And this has to do with, I mean, when you think about the heat transfer rate out of a fluid or out of the hot fluid and into the cold fluid, well, that's going to be a function of the capacity rates that are associated with the two fluids. So that's when we write that the effectiveness is a function of this capacity rate ratio, it takes into account the two capacity rates that are a part of the fluid or part of the system of the two fluids that are flowing through the heat exchanger. The effectiveness is also a function of the number of transfer units, because of the number of transfer units is defined as the overall heat transfer coefficient times the surface area divided by this minimum capacity rate. The overall heat transfer coefficient is an expression of that resistance due to conduction and those two resistances associated with convection for the hot and the cold fluids that are flowing through the heat exchanger, and of course the surface area. So this expression of the effectiveness being a function of these quantities, if we define the effectiveness as Q dot over Q max or Q dot max, we can use this relationship to relate to some other quantities in a given problem where we're defining the number of transfer units and this capacity rate ratio. Now, in order to use this effectiveness NTU method, we have to define and calculate some quantities, the effectiveness NTU and the capacity rate ratio, and we can use them with these expressions that we call the effectiveness relations. That is just an expression of the effectiveness as a function of these two quantities here, NTU and the capacity ratio. Now, to do that, we refer to other figures that have equations associated with them. So this expression here, this is table 11.4. And here you see these expressions for different heat exchanger types. Here's the double pipe, parallel and counterflow, shell and tube, with the number of passes and number of shells indicated for particular expressions that are going to be used. Also the cross-flow heat exchangers, both fluids unmixed, mixed and unmixed. But now here we have different expressions for mixed and unmixed, where if the one that's mixed, the fluid that is flowing on the outside of the tube, the cross-flow, if it has C max, we would use this expression. If the one that's the cross-flow is C min, we use this expression. And then, of course, we have, here's a special case one, when for all heat exchangers with C equals to 0, that means that if C is C min over C max, as C max approaches infinity, then C goes to 0. And the case where we consider C max going to infinity is where we have phase change occurring, because phase change occurs at a constant temperature. So essentially any delta T, essentially there's no delta T that's required in order for the heat transfer to occur. So the capacity rate that is the maximum would approach an infinity and cause C to go to 0. And so that just says anytime I have a heat exchanger, whether it's double pipe, shell and tube, or cross flow, if one of the fluids is changing phase, then we would consider C to go to 0, and we could just use a single expression to describe the relationship between the effectiveness, and it would now just be NTUs without the C there. Then that's basically, if you take this, the expression for heat exchanger number 4, look at the double pipe parallel flow heat exchanger, when C goes to 0, this expression just becomes 1 minus the exponential of minus NTU, and that we have a 1 in the denominator, and we have a 1 plus 0 multiplied by NTU. So this expression for the double pipe parallel flow heat exchanger reduces to this expression that is the last one here when C equals to 0. But for each one of these expressions of the effectiveness, they're written in terms of the number of transfer units and the capacity rate ratio here. Now, there is another table, table 11.5. It's exactly the same information, but it's rearranged so that the number of transfer units is written in terms of the effectiveness and the capacity rate ratio. So it's very similar to, hold on a second. It's very similar to the saturation tables that you found in thermodynamics. The saturation tables for water, in the text that I use, there are tables A4 and A5. Same information, one presented as functions of temperature, the other one presented as functions of pressure. Table 11.5 is just NTU written in terms of effectiveness and capacity rate ratio. Table 11.4 is effectiveness written in terms of NTU and capacity rate ratio. Ricardo, these tables are not in the appendix. So all of these expressions, though, are just used to define the heat transferred between the two fluids. If I have an expression for the effectiveness where I'd select it from that table, if I rearrange the effectiveness expression, it says that Q dot, the actual heat transfer rate, is the effectiveness times Q dot max, where Q dot max is the minimum capacity rate ratio times T hot N minus T cold N. And we still have the expressions that say that Q dot hot out of the hot fluid is the capacity rate of the hot fluid times T hot in minus T hot out. And the heat transferred into the cold fluid is the capacity rate of the cold fluid times T cold out minus T cold in. So the effectiveness NT method is just used to define this heat transfer that occurs between the two fluids so that we can write expressions excuse me, so that we can write expressions that define the heat transfer that is occurring between the two fluids. We can always define the amount of heat that is transferred out of the hot fluid by this expression and into the cold fluid by this expression, but the heat transferred between the two fluids is what we'd be interested in if we want to take into account here if the effectiveness is a function of the number of transfer units and the capacity rate ratio. This is where we get into the number of transfer units is where we can include the geometry or the configuration of the heat exchanger into our calculations, in that we have this overall heat transfer coefficient and the surface area for heat exchange that occurs between the two fluids while it's inside of that particular heat exchanger. So let's look here at a problem where we consider a shell and tube heat exchanger. Where we use the effectiveness NTU method to calculate a given quantity. Here, I want to consider the surface area. What must be the surface area if I know the overall heat transfer coefficient? So it's just a little variation from the previous problem. We used a log mean temperature difference method with a known surface area, and we sought to find the overall heat transfer coefficient. For this one, we'll consider, well, for a given overall heat transfer coefficient, how do we get the surface area? So this shell and tube heat exchanger that we'll consider that it has 2 shell passes and here 8 tube passes. So what does this look like here? So if this is my shell with an inlet and an outlet, if it has 2 shell passes, here this will just be a barrier, a solid baffle. So the fluid comes into the shell, flows along the length once, along the length twice, and comes out. 8 tube passes. Yeah, this will be 1, 2, 3, 4, 5, 6, 7, and 8 tube passes here. So fluid comes in and goes out. So that as the fluid moving through the shell is moving through the entire shell, it's also moving over these tubes, so that there's heat exchange between the two fluids that are passing through the shell and tube heat exchanger. And here we're going to consider that the cold fluid is ethyl alcohol. And this ethyl alcohol has a specific heat that is 2,670 joules per kilogram Kelvin, and is heated from 25 degrees to 70 degrees while it's flowing at a rate of 2.1 kilograms per second. So when we look here, we have all the information that we would need to calculate the amount of heat that's being transferred into the fluid. We have the mass flow rate, we have the temperature difference that it experiences, and we have the specific heat. Here, the hot fluid is water, and we'll consider its specific heat to be 4,190 joules per kilogram Kelvin. And it, since it's the hot fluid, it'll decrease in temperature from 95 degrees to 60 degrees C. The overall heat transfer coefficient is 800 watts per meter squared Kelvin here. And we'll consider that for this particular the cold fluid is the one that's running through the tubes here. So this is the tube. So right in a different color here. This is the tube fluid, and the water is running through the shell. So here we have the ethyl alcohol running through the tubes with the water running through the shell, so that we provide this heating to the fluid, and we want to determine, well, what is the surface area for heat exchange? Now here, since this is a shell and tube heat exchanger, all of the heat exchange would occur between the ethyl alcohol and the water through the tube, or through the tube that the ethyl alcohol is flowing in. The shell is just there to contain the water. So if I imagine here the cross section of the tube, here I'd have the ethyl alcohol on the inside and the water on the outside. And if you're trying to facilitate heat transfer, this wall has to be very thin in order to reduce the conduction resistance. And so the surface area, in a problem like this one, we would consider the surface area on the inside of the pipe, well, the perimeter on the inside of the pipe and the perimeter on the outside of the pipe are the same, or essentially the same, because all the heat transfer would occur along this entire length of the tube that is inside of the shell, where we have water and ethyl alcohol, such that heat is being transferred from the water into the alcohol to heat the alcohol. So the surface area that we're calculating, we could write as pi times d times L. So when we calculate this surface area, depending on what the diameter is of the pipe and the length of the pipe, pi dl would be this surface area that we're actually calculating here. Now, this overall heat transfer coefficient is the average value of the heat transfer coefficient that represents the resistance to heat transfer by convection from the water to the outside the conduction through from the outside to the inside, and the convection from the inside surface into the alcohol here. So when we define this expression, the expressions that we need here, we know that the heat transfer rate into the hot fluid is the capacity, I'll write these, m dot C sub P T hot in minus T hot out. And Q dot for the cold fluid is the mass flow rate times the specific heat times T cold out minus T cold in. Now here, the cold fluid, we have all of the properties we need. We weren't given the mass flow rate for the hot fluid. But because we're given the delta T and the specific heat, we can solve for that after we solve for the heat transfer rate into the cold fluid. So here I'll just make substitution of quantities here. The mass flow rate is given as 2.1 kilograms per second for the cold fluid. The specific heat is 2,670 joules per kilogram Kelvin. And the temperature difference here, T cold out 70 degrees minus 25 degrees C here. And so we can calculate then the heat transfer rate that is into the cold fluid, which would be equal to the heat transfer rate out of the hot fluid, which is equal to the heat transfer between the two fluids. So here, 2.1 times 2670 times here. All right, so times. All right, so I get here 252,315 watts is the heat transfer rate into the cold fluid. That heat transfer rate into the cold fluid is also equal to the heat transfer rate out of the hot fluid. So if I wanted to find the mass flow rate of the hot fluid, I could, because I have the specific heat and I have the temperature difference with this heat transfer rate that is into the cold and is also out of the hot fluid. But now if I want to get the surface area for the heat exchanger is going to come from an expression that allows us to, if we're using the effectiveness NTU method, the surface area is in the definition of the number of transfer units. So here, the effectiveness NTU method says that the effectiveness is Q dot over Q dot max, where Q dot max is the minimum capacity rate times T hot in minus T cold in. Well, we already have Q dot. We just calculated that's the amount of heat that goes into the cold fluid. So we have that quantity. The minimum capacity rate says we just need to find, well, what is the capacity rate of the hot fluid? What is the capacity rate of the cold fluid? And just compare the two. Well, the capacity rate of the cold fluid is 2.1 kilograms per second times 2,670 joules per kilogram Kelvin. So here that value, 2.1 times 2670, that is 5,340 watts per Kelvin. Now, what is the capacity rate for the hot fluid? Well, the capacity rate for the hot fluid is Q dot hot over T hot in minus T hot out. Well, the heat transfer rate out of the hot fluid is the same as what went into the cold fluid. So that's 252,315 watts. And the hot inlet temperature was 95 degrees. And the hot outlet temperature is 60 degrees. So that quantity of 252,315 divided here by 35 degrees is 7,209 watts per Kelvin. So the capacity rate of the cold fluid is the lower of the two. So this expression would be my minimum capacity rate, and this will be my maximum capacity rate. As we're just comparing the two quantities that are the capacity rates. So here the effectiveness can be defined for this heat exchanger, and that is the heat transfer rate of 252,315 watts divided by the minimum capacity rate here, which is 5,340 watts per Kelvin, times T hot in. The hot inlet temperature was 95 degrees. The cold inlet temperature was 25 degrees. So here we can find the effectiveness of this heat exchanger for the effectiveness NTU method. So here this is, see, divided by here 5,340 times 95 minus 25. And here this value is 0.675 is the effectiveness of the heat exchanger. So now with the effectiveness defined, we can write an expression for the effectiveness, and the capacity rate ratio is just the minimum capacity rate over the maximum capacity rate. The minimum is 5,340. The maximum is 7,209. So here, 5,340 divided by 7,209. And so this is 0.7407. So with these two quantities, we can write the expression that will allow us to solve for that surface area, 5607. Let's see here. 5607. 5607. I'm not sure what's being referred to as 5607. So here, this expression, in order to get a surface area, recall that the number of transfer units is the overall heat transfer coefficient times the surface area over the minimum capacity rate. We found the minimum capacity rate. We're given the overall heat transfer coefficient. So we need to find the number of transfer units so that we can write an expression that says that the surface area will be equal to the number of transfer units times the minimum capacity rate over the overall heat transfer coefficient. So for the expression of the number of transfer units for a heat exchanger that is a shell and tube heat exchanger with 2 shell passes and 8 tube passes. We go back to the figures here. We wanted to find the number of transfer units for a shell and tube heat exchanger. This is 1 shell pass, 2 or 4. So we have 2 shell passes and 4 to the end pass. So here, we have 8 tube passes. So these expressions apply for all of these expressions here. 4 times n will give us that 8. So here, the number of transfer units is n times n to u1, where n to u1 is this expression. And we found the effectiveness of the heat exchanger and the capacity rate of the heat exchanger. And so we would plug the values for the effectiveness and the capacity rate into this expression for the shell and tube heat exchanger to calculate the number of transfer units for this heat exchanger that is a shell and tube. And so once we substitute those values in, we can solve for the number of transfer units for the for this heat exchanger. So again, the only thing that we have to substitute in is the effectiveness and the capacity rate ratio to find NTU. So I'll just finish this up on Monday. But once we have that value calculated from the equation in that figure or that table, we have the minimum capacity rate and we have the overall heat transfer coefficient. So that allows us to then solve for this surface area here. Let's see here. CC should be 5607. 2.1 times 2670. Oh yeah, I left off the 0.1. So yeah, I'll fix that for the next class. All right, well, that's it for today. Just in preparation for the exam this next Wednesday, because I won't cover radiation until Monday. Radiation won't be on the last exam. We'll still cover it, but the only through chapter 11, the heat exchangers will be on the exam. All right, that's it for today. I hope you enjoy the rest of your day, and I will see you on Monday.